this lesson is going to be an intro to acids and bases and the theories that we use to explain how they kind of work. So an acid is defined as any solution, aqueous solution, where the hydrogen ion concentration is greater than the concentration of the hydroxide ions. And a base is kind of the opposite. In a basic solution, the concentration of hydroxide ions is greater than the concentration of hydrogen ions. This little chart right here kind of shows that it's kind of a spectrum. We can go from one to the other, and we've learned that in our lab that the litmus paper is a test that we use to test for acids and bases, and in an acid, litmus paper turns a pinkish red color, and in a base it turns sort of a bluish color. And it's not sometimes as simple as saying whether something is an acid or a base. There's sort of a spectrum in between there. There's shades of gray, and we're going to talk more about that as we go along. The key idea here is that a base or an acid are something that pushes water's equilibrium one way or another. What do I mean by water's equilibrium? Here's what I mean right here. Water is, as a pure liquid, in a beaker of pure water, a very small amount of that water is going to change into hydrogen ions and hydroxide ions. So the stoichiometry here, let me change my pointer. The stoichiometry here is a one-to-one sort of stoichiometry. So we know that in pure water, the concentration of hydrogen ions is always going to be equal to the concentration of hydroxide ions, because if one of these breaks up, it's going to give me one of those and one of those. So these concentrations are always going to be equal. It doesn't happen very much. If you take a look at the equilibrium constant for this, the factor there is times 10 to the negative 14th. That's a very, very small equilibrium constant, and we call it Kw because it's the equilibrium of water. We get the special letter W. And so this doesn't happen very much. Now, if we look back at this, this is actually a heterogeneous equilibrium. It's kind of like a solubility equilibrium. We've got liquid water here, which wouldn't be included in this in the equilibrium expression. So what the expression actually ends up looking like is the concentration of hydrogen times the concentration of hydroxide ions is equal to that constant 1 times 10 to the negative 14th. And that has got to be true at all times in any aqueous solution. It never changes from that value. So an acid is something that increases the concentration of hydrogen ions, and that would mean that it lead to a decrease in the concentration of hydroxide ions. If hydrogen ions go up, then the hydroxide ions have to go down in order for this to stay 1 times 10 to the negative 14th. That's the way that this equilibrium works. Now, for purists out there, for people who are going to come on to this and look at this video and say, well, actually, hydrogen ions don't actually exist by themselves. If you think of a hydrogen ion by itself, an H plus ion, what that really is a proton. There's no electron. It's the simplest atom, so it's just a proton. That never actually exists in the solution. What actually happens is that the water breaks up, and you can notice that there's two of them in this one. That the hydrogen comes off of there and joins onto another water. So rather than making hydrogen ions, what you're actually making is the polyatomic ion hydronium. And hydronium is the same sort of thing as hydrogen ions. These two things are really used interchangeably. Hydrogen ions and hydronium ions pretty much mean the same thing. If you want to be really picky about it, there aren't any hydrogen ions, it's only hydronium. So when we talk about this in class, I'm going to try to switch back and forth kind of intentionally because I want you to be adept at doing it and thinking about them either way. So the models that we use for our acids and base reactions go back about a little over 100 years. The first model we used was called the Arrenius Model, and what this model says is that anything that contains hydrogen that can ionize and form hydrogen ions or hydronium ions is an acid. And it also furthermore goes on to say anything that can ionize to form hydroxide ions is a base. And that seems to work pretty good for things like hydrochloric acid. It explains very easily why that's an acid. And sodium hydroxide, when it ionizes, forms hydroxide ions, and so that explains why it would be a base. And that seemed to work pretty good until you start to think about some of these other bases, like, for example, ammonia. NH3, nitrogen trihydride, otherwise known as ammonia, is also a base. And so if you think about this using the Arrhenius model, it's pretty tough to come up with a reason why this would be a base. There's no hydroxide ions in ammonia. When it ionizes, it doesn't really ionize, and so, or at least not the way that we think about it here. It doesn't make hydroxide ions. So why would that be a base? We obviously needed to rethink things and come up with a new model. The model that we use oftentimes in chemistry still to this day, although there's another one since then, is called the Brønsted-Lowry Model. And in the Brønsted-Lowry Model, it doesn't worry about hydroxides. It just focuses in on the hydrogen ions or the hydronium ions. Okay? And what an acid is anything that will donate a hydrogen ion, that can give up a hydrogen to something else. And a base is something that accepts a hydrogen ion. So the Brønsted-Lowry model is about passing a hydrogen ion back and forth between two compounds. The one that gives it is the acid. The one that receives it is the base. And in this model, we can explain the behavior of acids. So, for example, nitric acid, hydrochloric acid, and chloric acid can all be explained because they're going to ionize and give hydrogen ions to somebody. When we go through these in class, oftentimes in order to talk about acids, we'll just simply say an acid is HX, where X could be any of these anions like nitrate, chloride, chlorate. In this case, it could be sulfate, which would be a -2 charged ion. And any anion could be represented by X. Okay? So let's try and write a reaction between an acid and a base. When we talk about Brønsted-Lowry acid-base reactions, if we've got an acid in there, we just automatically assume the other thing is a base. Here we go. We'll make a generic acid like HX, and we'll put it in water. How does that acid make water into an acidic solution? Well, when it gets into water, the hydrogen hops off of the anion X and joins up with the water and makes hydronium. That's what's making this solution acidic, and then what's left behind is the X anion, whatever anion that might be. So because this thing is giving a hydrogen to something else, it is an acid. But that begs a kind of a goofy question. If that's an acid, wouldn't water in this case be a base? It seems kind of weird, but to think of water that way, water is neutral. It's not an acid or a base. But water is a base when you put it with Brønsted-Lowry acid. We treat all of these reactions like it's a reaction between an acid and a base. HX is clearly an acid. That means water must act like a base in this reaction. So now, if that's the acid and the base for the forward reaction, let's look at what they would be in the reverse reaction. In the reverse reaction, this thing is the thing that's going to take a hydrogen and change back into HX. So in the reverse reaction, that is the base. This is going to give a hydrogen ion. The hydronium is going to give up a hydrogen ion and change back into water in the reverse reaction. So that would be an acid. The ones on the right side of the equilibrium, the ones kind of for the reverse reaction, we call the conjugate acid and the conjugate base. And you need to be able to identify them as pairs. So in this particular reaction, the hydrogen is passed back and forth between this acid, HX, and the anion, X minus. They are linked together by the passing of a hydrogen back and forth. HX is the acid, X minus is the conjugate base. That X ion is the conjugate base. On the other side here, the flip side of this thing is that our water is acting like a base in this reaction, and then the hydronium is acting like an acid in the reverse reaction. But you could change water into hydronium by giving it a hydrogen. You could change hydronium into water by taking away a hydrogen. By simply passing a hydrogen back and forth, these two compounds change into each other. They are linked. They are conjugate acid-base pairs is what we say. Water in this case is the base. Hydronium is the acid. And so let's go back and look at ammonia. Remember, the reason we had to come up with this is because the Arrenius model didn't explain why ammonia would be a base. So the ammonia molecule, when paired with water, takes a hydrogen from water and changes into the ammonium ion, and that makes hydroxides. So since ammonia is a base, water acts like an acid in this case, and it makes hydroxides. This is why ammonia, when you put it in water, gives you a basic solution, because when you put it with water, it robs the hydrogen from the water, leaving the water as hydroxide, and those hydroxides increase the amount of hydroxide in the solution, which makes it basic. And in this case now, ammonium is the conjugate acid, and the hydroxide is a conjugate base. Ammonium could give a hydrogen. It's got an extra hydrogen to give, and the hydroxide ion could take a hydrogen and change into water, so it would be a base. Those two are linked together as acid-base pairs. Again, water and hydroxide, and ammonia and ammonium. So we had water act like an acid here. In the previous slide, we had water act like a base. Water is a compound that we call amphoteric, which means that it can do either. It could be an acid or a base, and it really depends on what you have it with in a solution as to whether it will act like an acid or a base.